my pleasure to introduce our next lecturer. The danger, of course, in introducing Andrea Goldsmith is that there's so much to say that I could probably use all of her time. And then we'll all be disappointed to listen to me instead of her. But let me just tell you a little bit about Andrea. Andrea got all of her degrees from Berkeley. I'm trying not to hold that against her. And has had faculty positions at Caltech and at Stanford, where she's currently a professor. She is the founder of Quantenna, or one of the founders of Quantenna. She's been an editor for both communications transactions and information theory transactions. She has received the NSF Career Award, as well as Sloan Fellowship, and many other awards, which I won't attempt to list. And her talk today will be on seeking Shannon capacity for wireless channels and networks. Thank you, Andrea.
Thanks very much, Michelle. Thank you. It's a pleasure to be introduced by my longtime friend, colleague, and the cohort at Caltech as the first women faculty in their electrical engineering department. Thank you very much for inviting me to the organizers. I'm hoping to impart to you kind of a high-level view of what it means to seek Shannon capacity for wireless channels and networks. The channel part is a little bit better defined than the network part, and I think that's one of the exciting areas of research in information theory, is not only seeking capacity of wireless networks, but defining it. And I think that that problem requires a broader set of tools and more interdisciplinary interactions than perhaps some of the work that's gone on the last several decades in looking at Shannon capacity of channels. So let me start out by, why is it interesting to look at Shannon capacity or fundamental limits of wireless channels and networks? And the motivation is really the future of wireless, which has many exciting applications beyond just next generation cellular and internet access, but also device-to-device communication, sensor networks where energy is a major constraint, which is something that hasn't come in too much in Shannon capacity analysis, either in terms of transmit energy or processing energy, as well as applications like automated highways and automated factories and smart homes and smart grids, where delay becomes critical. And that's another area where Shannon capacity hasn't had too much to say in terms of gaining design insight. So why am I starting with this picture as motivation? I think in Shannon's brilliance in the 1940s, when there was really no such thing as an integrated circuit or VLSI, and analog communications was the way everything was done, he had the foresight to look at fundamental limits of wireless channels and networks. And it took decades, actually, for the technology to catch up to the insights that he provided through that mathematical framework. And now, certainly on static, white Gaussian noise channels, we achieve Shannon capacity for all intents and purposes. And a lot of the insight into the design of those systems comes to some extent from Shannon's work. But in the context of the networks that I've shown on this picture, we don't have a lot of fundamental results, which means we don't have a lot of fundamental insights into optimal designs or even bounds to compare the designs that we have against. And so I think that there's a huge amount of work to be done in coming up with fundamental limits, not just because it's a lot of fun and very satisfying, but also because in terms of practical designs, we can gain a lot of insight and avoid missteps by determining these fundamental limits and the technologies underlying them. So like I said, one of the things about the future that I think is interesting is when we go to device communication, we're not just going to be pushing higher data rates, but we're going to have to bring in things like delay and energy constraints, and that opens up new problems as well. So the challenges in terms of building these future wireless networks, for the purposes of this short course, is that fundamental capacity limits of wireless networks, not only are they not known, so if you don't know what the limit is, you can say, okay, you can work on determining the limit, but in fact, they're not really very well defined. And I'll go into that more in the second half of my lecture. So formulating the problem, which is always true in research, is one of the hardest parts of coming up with these fundamental capacity limits. As a result of having very few fundamental results on limits of wireless networks, wireless network protocols, and maybe there's people doing research on this in the audience, but I would venture to say that most of these protocols are very ad hoc. And the way they determine if you have a good protocol is, well, my protocol is 10% better than the state of the art in the literature, so it's a better protocol. But that doesn't mean that it's anywhere close to the best that we could possibly do in terms of protocol design. So not having these fundamental limits not only doesn't give us insight, but it doesn't give us a way to compare the protocols that we design against, so that, you know, when you're a fraction of dB away from the capacity limit, you can rest and go home and have a glass of grappa if you're with Roberto, and not worry about doing more research. But if you're orders of magnitude away, then you probably need to keep working. The other thing that Shannon Capacity doesn't weigh in on very much is applications that are heterogeneous, that have different requirements, not just in terms of data rates, but particularly in terms of delay constraints and outage constraints and energy constraints. And so how do we bring those constraints into our analysis of fundamental limits? So these are some of the things that, again, I'm going to start in the first hour or so of the talk discussing more single user channels and multi-user channels where we have a lot of results and we have a lot of insight. And in fact, current wireless systems are being designed based on a lot of this insight. The second half of this talk, I'm going to go into the more nebulous territory of wireless network capacity, how to define it and how to bring in these different constraints. Okay, so let me start by talking about what is wireless channel capacity. And when you have a multi-user channel, so you have, say, a transmitter sending to many users or many users sending to a single receiver, capacity is defined as the set of simultaneously achievable rates, so the rates that you can get to all users at the same time. It doesn't mean that some users don't have to wait as they average out their data rates, but on average, these are the rates that we can get. And the main drivers of the channel capacity are the bandwidth available. That's why companies pay billions of dollars for spectrum, because the more spectrum you have, the higher data rates you can get. It also depends a lot on the receive power at each transmitter, and that's dictated by not only the transmit power, but also the characteristics of the channel that you're transmitting over. Now, in wireless systems, the channel tends to be dynamic. So it changes randomly according to some statistics, and the dynamics of the channel, whether it changes quickly or slowly, has a lot of impact on the capacity. It dictates how well we can estimate the channel, if we need a channel estimate at the receiver, or if we want to feed back that estimate to the transmitter to adapt. Then the dynamics dictate how quickly we can feed it back, how outdated the information is. It also dictates, if we have a delay constraint, whether we can average over many channel realizations if the channel is changing quickly relative to the delay constraint, or if the channel is relatively static and you happen to get stuck in a deep fade, how do you define capacity under those circumstances? Because you have to drive probability of error to zero in a typical definition. In addition, capacity of dynamic channels depends on what's known about the channel at the transmitter and or the receiver. Often we make assumptions that the channel is known based on some genie that gives us the channel or some separate channel that's doing the estimation. Feedback, another unknown dimension to a large extent in terms of capacity, even of single user channels. Antennas have a big role to play as well. And then whether you have flexibility in terms of the rate, if you need a given rate all the time, or you can average your rate, and also delay constraints. So there's many, many different parameters that dictate the capacity of a wireless channel. And then when we go to network capacity, so the kind of Shannon definition is similar. It's the set of all rates. But now you've got n different nodes talking to n minus 1 other nodes. So you have a rate region that's a very large dimension, n times n minus 1 dimensional. And so the capacity is the fundamental limit of these sets of rates. Usually we try to go for upper and lower bounds and then try to show that they meet. And of course, you may have other axes as well that aren't just based on capacity, but potentially with some delay constraint or energy constraint. So again, I'll be talking more about network capacity in the second half of the talk. If we want to investigate fundamental network capacity, which is what I call the Shangri-La of information theory. So Shangri-La is defined, for those that don't know, it's an earthly paradise permanently happy land, isolated from the outside world. So if we actually could derive the Shannon capacity of a network, we'd be pretty happy. We might win lots of paper awards. Not clear how useful it would be because it depends on the definition and the insights that we get. But nevertheless, that's what I'm going to call the Shangri-La of information theory. But it's really quite far away from where we are today. We have made a lot of progress in finding the capacity limits of wireless single-user channels and multi-user channels. But we have very limited understanding about the capacity limits of wireless networks, even for simple models. In the most simple of models, the relay channel, 3 nodes, okay, 1 transmitter, 1 receiver, 1 relay, has been an open problem for decades. Okay, so if we can't solve for the capacity of the most simple wireless network we can think of, what is our hope of coming up with good capacity bounds for networks of 5 nodes or 10 nodes or 100 nodes like we typically want to see in some of the applications that I described? Again, as I mentioned before, bringing in energy and delay constraints, hard constraints, may require new definitions of capacity. If you have a hard energy constraint, for example, you can't talk about bits per second because bits per second assumes bits per second for all time. But if your battery runs out and you can't recharge it because you have a hard energy constraint, bits per second is no longer a good metric. Maybe you should be talking about energy per bit. And then, of course, the amount of lifetime of the node will come in because you can have lower energy per bit if you send your data over a longer period of time. So what is the right definition when you bring in these hard limits is to some extent an open question. And then again, is this the right goal to pursue? That's something I'll talk about again towards the end. Okay, so let's start with in the beginning, at least in the beginning of information theory, there was Shannon. And he had the brilliance to develop a mathematical theory of communication for digital communication systems. Again, at the time, all communications was analog. But he had done a lot of work in the military and had worked on digital systems and began speculating on what are the fundamental limits of a digital communication system. One of the beauties of Shannon's theory, which I think still holds today, is that it's a fundamental characteristic of the channel. So it is independent of transmission and reception strategies, which means that it doesn't matter if us engineers are really creative or not at all creative in terms of coming up with ways to do modulation and detection. It doesn't matter if you have really powerful VLSI chips that have infinite complexity. The Shannon capacity is independent of all that technology. And the beauty of that is that it really is a truly fundamental upper bound that we can strive to achieve, and as technology evolves, we can get closer and closer to that fundamental bound. So Shannon capacity depends only on the channel characteristics as well as the various assumptions that you make about the system, like do you have channel information and so forth. Shannon capacity for stationary anergodic channels is the channel's maximum mutual information. And the significance of capacity, so it's a mathematical construct, this mutual information, which I'll define in a moment. The significance is not that he defined mutual information in this mathematical way. It comes from his coding theorem in Converse, which basically shows that the capacity of a channel is the maximum data rate you can get over that channel with the probability of error as small as you want. So you can make the probability as close to 0 as you like as you increase the block length and therefore the delay of the system. So let's talk a little bit about Shannon capacity. If you have a discrete memoryless channel and the input to the channel comes from some alphabet script X, and the output is constrained to be from some alphabet script Y, these can be uncountably infinite alphabets or finite alphabets, then the channel has mutual information defined by this expression here. So the mutual information, average mutual information of the channel with this input and output alphabets is the sum over all possible inputs and outputs of the joint probability of those particular input and output times the log of the joint probability divided by the individual probability. So that's the mathematical definition of average mutual information. And again, the sum is over all possible inputs and outputs. What Shannon proved is that for a discrete memoryless channel, the capacity is equal to its maximum mutual information. So this is the mutual information defined here. And you maximize over what you have control over as a designer, which is the distribution of the input. So you maximize over all possible distributions for your input alphabet, and that gives you the capacity of the channel. Okay, so I said that the beauty or the importance of this result is in the coding theorem in Converse. So let's start with the coding theorem. Basically, the coding theorem says that for any rate less than capacity, so for any epsilon, no matter how small, sorry, I think that should be delta. Anyway, for any rate less than capacity, with probability of error approaching 0, so there exists a code. Some code exists with a rate as close to capacity as you want that has a probability of error that approaches 0 as the block length of the code grows. And Shannon didn't actually provide a real code, so he didn't provide a code with this property. He proved that a code existed. And the way he did that was through a random coding argument. So he generated a code according to the random distribution that gives you the maximum mutual information. So I said there's some maximum probability of X, which gives you the capacity. So Shannon generated a code according to that distribution. And for any block length, he showed a decoding whereby as the block length goes to infinity, the probability of error goes to 0. Now, generally, when you prove these coding theorems today, you use something called typical set decoding. And the idea of typical set decoding is that, so you're the decoder, you're looking at the output of the channel. So you get some realization YN's output from the channel. And you're trying to figure out what was the input sequence, what was the XN, what was the code word that gave me this output. So the notion of typical set decoding is you look at the output and you say, let me find all possible input code words, X to the N, that are typical with my output, which basically means that X to the N has an entropy, has the probability of realizing that Xn close to its entropy, probability of the output Yn being close to its entropy, and the joint probability being close to its entropy. Okay, so by something like the law of large numbers, in the limit as the block length goes to infinity, as long as you're generating the code according to this random coding argument, the probability of error, in other words, the probability that you pick an Xn, that there's more than one Xn, or that you pick the wrong Xn that's jointly typical with Y goes to 0. So this is how most of these proofs are done in the literature today, according to these kinds of random coding generation and typical set decoding. But Shannon's proof in his 1948 paper has a similar intuition, and I really recommend everybody read that paper because it's a beautiful paper and it's a beautiful proof. He just used the notion of geometry. So the idea is that, so this sphere is, sorry, it's a little cut off here, is representing all possible outputs. So it's an n-dimensional sphere corresponding to all possible y to the n's, the outputs of your channel. And the black dots here are the code words x to the n that would be generated by this random code. And basically, Shannon's proof shows that, first of all, the volume of this sphere, as n goes to infinity, is concentrated around the perimeter of the sphere. And basically, he showed that for any xn that you transmit, the noise or the uncertainty associated with decoding that xn correctly is shrinking into a ball around with the center at the code word. And basically, in the limit as n goes to infinity, these circles become disjoint. So you can't make an error in your decoding because you're only going to see something in one of these circles corresponding to the code word in the middle that was transmitted. And if the circles are disjoint and they correspond to what you receive, you can't make an error. So it's a similar idea as the typical set decoding, but it's very visual and much simpler to understand. There's no math to it. It's just a geometric proof. Okay. Now, the converse uses the workhorse of converses to coding theorems, which is Shannon's inequality. And the idea of the converse is that if you have, so the challenge of proving converses is that you have to prove that for any transmission scheme, no matter what it is, the probability of error is bounded away from 0 if the coding scheme has a rate above capacity. So the reason it's challenging is that you don't just have to come up with a good scheme that has good performance. You have to prove that every scheme, no matter what it is, will have a probability of error bounded away from 0 if the rate is too high. So the way that most of these proofs are based on is Fano's inequality, and the idea is that you have some message W that your coding scheme is going to send through the channel, whatever the coding scheme is. And the rate of the transmission is equal to the entropy of that message. And you can break it down into the entropy of the message condition on the output. Sorry, this should be raised to the n. And the entropy and the mutual information between the message and yn. Okay? So you can now say that because W is a function of the input, so your input is mapping to the message, you can write this in terms of the mutual information. So you just write this IWN in terms of the mutual information between your input and your output. And then you apply Fano's inequality. And Fano's inequality says that the entropy between your message and your output has to do with your probability of error. And that makes sense intuitively, because if you could decode the message perfectly, your probability of error would be 0. So the uncertainty or the entropy between those two is a function of the probability of error. So this is Fano's inequality, and then I just have the same term here. Okay? Now, this implies, so the reason Fano's inequality is so important and so much a part of these theorems is that it gives you a way to connect probability of error to the mutual information. So basically, this set of inequalities implies that the probability of error is bounded above by this expression, okay? Which means that the error is bounded away from 0 for r greater than c. So in other words, if you come up with any scheme that maps your message W to a code of rate r, and that rate is bigger than capacity, by Fano's inequality, the probability of error is bounded above. Okay, so Fano's inequality has been used a lot for single user channels and also for multiple access and broadcast channels. The problem is that it's not tight when you go to larger networks, and that's been one of the challenges in coming up with capacity of networks, is that we don't have good tight upper bounds on the capacity. Okay, so now let's, so that's kind of the general theory, and I'm not going to go into this level of detail with the other capacity results, but most of what I've talked about is fairly easy to extend to multi-user channels, or at least some of the same ideas apply. And now I'm just going to give you some of the results. So starting with the most basic of channels, the additive white Gaussian noise channel. So you have an input X, output Y, additive white Gaussian noise sample that's added to X. We're going to assume, first of all, that this N is a Gaussian process. It's a white Gaussian process, so samples of it are IID. We're going to assume some bandwidth B for the channel, and the receive power is P. So the signal to noise power ratio, which is something you should all be familiar with just from undergraduate communications classes, is just the receive power P divided by the total noise power in bandwidth B, which is N0B, where N0 is the power spectral density of the Gaussian process that we started out with. Okay, so the maximum mutual information, just applying Shannon's formula to this channel, gives us the famous capacity formula that capacity is equal to the channel bandwidth times log 2 of 1 plus the signal to noise ratio, and that's in units of bits per second. So this is a very simple formula. Where it comes from is, again, if I go back 3 slides, it's maximizing this mutual information. So now X has some distribution. Y is equal to X plus N, where N is Gaussian. You can show that the maximizing distribution is Gaussian, so the input is Gaussian. You add to that noise, which is Gaussian, so the output is Gaussian. So now all these distributions are Gaussian, and you can go ahead and compute the capacity as this formula. Okay, so I haven't told you anything about wireless channels yet. Additive white Gaussian noise channels are not, in my opinion, wireless, although they're the most basic wireless channels. So let's talk about wireless channels now, okay? So in a wireless channel, by the laws of physics, the receive power diminishes with distance according to either a free space path loss formula if you've got no reflections, or you can have a more complex power fall off with distance according to ray tracing or whatever model you like. Now, the other thing that happens in wireless channels is multipath. So you have signals that are reflecting off building or objects. These come into the receiver delayed in time and shifted in phase from the direct path signal. So this gives rise to the fading that you experience when you're talking on your phone, and you move a little bit and the signal goes out, and you move a little bit more and the signal comes back. It's basically the constructive and destructive addition of these multipath components, because every time you move by a quarter wavelength, the phases realign, and so sometimes you'll have constructive addition of the signals, and then you move a quarter wavelength and you get destructive addition. So you get very dramatic fluctuations in your received signal strength, 30 to 40 dB, which is called flat fading. And you can also get frequency selective fading. So if this path is delayed by more than a symbol time, then the symbol that you transmit over the direct path will have interference from previous symbols coming over the delayed path. So now you're interfering with yourself in the form of intersymbol interference, and this gives rise to frequency selective fading, fading that in the frequency domain is not constant. Okay? So these are the two major difficulties or impairments that we have to deal with in wireless channels. Then, of course, they're dynamic channels because things are moving. So when you move a little bit, the multipath changes. Either it goes away or you get a different addition. We get blockage from objects, and also the radio is a broadcast medium, so everyone interferes, which is not the case when you're looking at wireline channels. So these are the impairments that we have to handle when we look at capacity of wireless channels and networks. Okay, so let's start with the flat fading channel. Here I have some gain, random gain, that at each time I has a different value, and I'm going to assume some distribution for that. So it's the same channel I had before, the additive white Gaussian noise channel. Here's my noise, here's my input, here's my output, but now I have this multiplicative fading. Okay, so now I have to bring in some other assumptions about the channel. The additive white Gaussian noise channel was simple because I only needed to know the noise power spectral density. Now there's some other things I need to define, like what is the distribution of the fading? Can I estimate the fading at the receiver? Do I want to assume any noise or delay on that estimate? Is there a feedback path that I can use to feed back the channel estimate to the transmitter so that the transmitter can adapt to the fading? So these are all fundamental questions that you have to answer before you can solve the problem, because they're fundamental to solving the problem. Okay, so when we look at capacity of flat fading channels, again, we have to define, first of all, what do we know about the channel and where. So suppose you assume you don't know anything about the statistics of the fading, that G parameter. We don't really know how to solve that problem because usually we make some assumptions about statistics. So we wouldn't have any idea really how to formulate the capacity of a channel that was completely unknown. We didn't even know the statistics. So we don't look at that problem. Now, when the statistics are known, so assume you know that G is Rayleigh fading or log normal shadowing. It's actually very hard to solve for the capacity of that channel. It's a simple model, right? So it's just going back. It's the additive white Gaussian noise channel with a multiplicative fading parameter whose statistics are known. So it doesn't seem like it's that much harder than solving the additive white Gaussian noise channel, but it turns out to be very difficult to solve. And in fact, as far as I know, capacity is only known for a few very special cases. One, when the fading is IID Rayleigh, so at each time instant you take G from a Rayleigh distribution and it's independent from time to time, which is not that practical a model. Or if the channel follows a finite state Markov model, in which case it has some structure that you can use to define the capacity. Okay, so in most practical systems, we measure the channel at the receiver. For all kinds of things, for demodulation, for feedback, and so forth. So suppose we assume that the fading is known at the receiver only, no feedback to the transmitter. Well, then the capacity formula looks a lot like a probability of error calculation. So when you're looking at the probability of error in fading, you take the probability of error in additive white Gaussian noise, and you integrate it over the distribution of the signal-to-noise ratio. So remember, this is the Shannon capacity of an additive white Gaussian noise channel with signal-to-noise ratio gamma. Now I'm integrating over the distribution of the signal-to-noise ratio, which, because the noise is constant in terms of its power, the signal-to-noise ratio distribution just depends on the distribution of the fading, which I know, and that gives me the capacity. The problem, though, is that if you looked at this formula, you might say, okay, so in terms of the capacity proof, the way I would prove this is that the additive white Gaussian noise channel capacity for each instantaneous gamma is going to change with gamma. But that's not possible because there's no feedback, right? What this formula says is that you're transmitting at a fixed rate equal to this average, and even though gamma is changing over time and you're transmitting at that fixed rate, you're still going to achieve this capacity with probability of error going to 0, okay? So the proof of this uses the maximum mutual information proof, average now over the input and output distributions with the fading as well. I won't go into the proof of that. One interesting thing to note here, by the way, is that if you only know the fading at the receiver, the capacity is lower than if you had an additive white Gaussian noise channel with the average signal-to-noise ratio associated with the distribution. That's this inequality here, which is just Jensen's inequality, because log is a convex function. Okay? So fading always hurts you in terms of capacity if you only know the fading at the receiver, not at the transmitter. Okay, so let's look at the case where the fading is known at the transmitter and receiver. This is actually work I started doing at the beginning of my PhD. And at that time, there weren't a lot of practical systems that did adaptation at the transmitter and receiver. And one of the things I looked at is this ever going to be practical? Is anybody ever going to implement, adaptation based on fading? And most wireless systems today do that. So 802.11 and cellular systems, they all adapt at the transmitter. So it's reasonable to say you're going to have a feedback path, because most practical systems do. They do estimate the channel and they feed it back. So what if we know the channel perfectly at both the transmitter and the receiver? Of course, you're not always going to know it perfectly, and there's delay, but I'm not going to get into that. Let's just focus on the case where you know the channel, okay? So if you keep the transmit power fixed, you don't change the transmit power, then knowing the channel at the transmitter does not change the capacity at all. Doesn't help you at all in terms of capacity. It helps you a lot in terms of transmitter and receiver complexity, similar to what happens in MIMO, as I'll talk about, but it doesn't help you at all in terms of capacity. What really helps you is if you can adapt the power. Because the idea is that you've got this fading channel with power that's going up and down, right? And you've got some average power constraint. What you'd like to do is when the channel is good, we're in LA, right? So it's like surfing. You ride the good waves, okay? So when the channel is good, you put a lot of power into the channel because the channel's already good. And that way, you can get very high rates when the channel's good. When the channel's bad, don't fight it. Don't waste your power trying to transmit over a bad channel, so you back off when the channel's not good. So that's the intuition behind why adapting your power makes a big difference. Okay, so if we know the channel at the transmitter and receiver, this is the capacity formula. So it's the same as the additive white Gaussian noise channel. So again, we have the B log 2 of 1 plus S and R. What's different now is S and R, so I still have my gamma, which is the S and R in fading, assuming a fixed power, S bar. And now I'm going to allow myself to adapt my power. So S of gamma is the power that I put into the channel when the channel has S and R gamma. And this is the expression. And I maximize the transmit power subject to an average power constraint. Okay? Now, in this case, the capacity proof is actually very simple, because all you do is when the channel has an S and R gamma, you use the additive white Gaussian noise encoder and decoder that's optimized for gamma. So when the channel changes state, you just change to a different encoder and decoder. The capacity then is equal to the capacity of the additive white Gaussian noise channel with S and R gamma and the transmit power that you put in. So at each time instant, or at each channel state gamma, this is indeed the rate that you get over the channel. So you're getting a variable rate transmission here you change your power and your rate to maximize this expression. Okay, so what does it look like when you do the optimization? It's a very simple Lagrangian multiplier problem. It's not a scary optimization. And when you solve for it, you get that the optimal S gamma over S bar is a water filling. So gamma now, again, is the instantaneous signal-to-noise ratio on the channel, assuming a fixed transmit power. When the channel's good, so large gamma, what I put into the channel is this water level 1 over gamma 0 minus 1 over gamma. So as gamma gets large, the bowl, this 1 over gamma, is going down, so I put more power into the channel. As gamma decreases, I put less and less power into the channel. And then at some gamma 0, I cut off. I don't use the channel anymore. It's not any good. And I don't send anything through the channel. So that's the water filling power allocation over time in flat fading. And the capacity is then just this simple expression. R over B is the integral from gamma 0 to infinity of log 2 gamma over gamma 0 times the probability of gamma. So that's the optimal adaptation scheme. And instead, so one of the problems of doing this is what I said before. You have variable rate and variable power. And that may not be practical in all systems. So one of the things that's also been looked at is the notion of channel inversion. Suppose we invert the fading to maintain a constant signal-to-noise ratio. This greatly simplifies the design, and this is the kind of thing you would want to do if you had a delay constraint on your channel. So you get a fixed rate. However, it greatly reduces the capacity. So this notion of channel inversion is what spread spectrum systems do for power control. They maintain a fixed power. The problem is that in severe fading like Rayleigh, you have to use so much power to invert the deep phase from Rayleigh fading that you basically have no power left over to transmit. A smarter way to do that is to truncate the inversion. So this borrows from the insight that you get under channel capacity, and you say, I'm going to invert the channel above some cutoff fade depth. So if the channel's really bad, I'm not going to use it. That gives me a constant signal-to-noise ratio above this cutoff, so I don't need to design these variable rate transmitters. I'm just transmitting at a fixed rate. And the cutoff greatly increases capacity over not doing any cutoff, so just doing the inversion. So this shows the capacity in flat fading for Rayleigh and log normal. This is basically the capacity of the additive white Gaussian noise channel. This is the capacity, the top line here, it's a little blurry, when you know the channel at the transmitter and receiver. And this dashed line here is when you know it at just the receiver. And this line is when you do the outage capacity, so you optimally truncate. And this line is when you don't do any truncation. So there's a couple things I want to point out about this curve. First of all, Shannon capacity, and I should have blown this up, is not always better than the capacity in flat fading when you adapt optimally. Okay, so there's a crossover here where this capacity actually exceeds the capacity of the additive white Gaussian noise channel with the same average signal-to-noise ratio. Why is that? Well, down at this part of the curve, when you're in very low signal-to-noise ratio, your channel's bad all the time in the additive white Gaussian noise case. In the fading case, it's also bad. In fact, it's really bad most of the time. But once in a while, you get a really good channel. And when you get a really good channel, you can put all your power into that case and blast out at a high data rate and therefore actually exceed the capacity of the additive white Gaussian noise channel. The interesting thing is that you don't do so much better than when you only have receiver side information. Okay, so the gap between these two curves is not that big. The problem is that the complexity of the receiver only decoding is very high. And again, as I said, in Rayleigh fading, capacity is 0 if you try to invert the channel no matter what. Log normal shadowing the picture is a little bit different, but again, the difference between knowing the channel at the transmitter and optimally adapting to it and not knowing it is not very much in terms of capacity, but it's a lot in terms of complexity. Okay, just one other quick point I want to make before I move on from these flat fading channels is that this intuition of Shannon capacity for flat fading channels translates directly to practical modulation encoding techniques. So the idea now is instead of looking at this as a capacity system, I'm going to look at it as an adaptive MQAM system. So I have BPSK, 4 QAM, 16 QAM, however many QAM I want. And I'm going to optimally adapt the modulator, the constellation size, according to the signal-to-noise ratio that I get, and I'm going to adapt my power as well. And the goal is to optimize the power and rate to instantaneous rate to maximize my average rate of this adaptive modulation system. So the optimization formulation, if you assume an approximation for the probability of error, actually gives you a formula that looks exactly like the capacity formula I showed before, except for this parameter k. K is the coding gain associated with the Shannon code, and K depends on the probability of error according to this formula here. So it's 1.5 divided by the natural log of 5 times the bit error rate. So you do this optimization, you get the exact same water filling power adaptation because it's the same formula, and the spectral efficiency, again, is identical to the capacity formulation with a power loss of K. So if you look at the spectral efficiency, this is what I get for my Shannon capacity with optimal adaptation. This is the capacity if I tolerate a probability of error of 10 to the minus 3. And this is the capacity with a probability of error of 10 to the minus 6. So the more stringent my probability of error, the farther I am from capacity. Is there a question?
When you say you know the channel, do you mean you know the statistics of the channel?
I know the channel. I know both the channel instantaneously, gamma, and I also know the distribution. And the place the distribution comes in is actually in the computation of the optimal cutoff gamma k, or gamma 0 in the capacity case. That's the only place where the distribution comes in. Because the water filling, if you see, sorry, this is a little misplaced, is, let me go back to the capacity one. The optimal power adaptation doesn't depend on the distribution at all, right? It only depends on the cutoff value, gamma 0, and the instantaneous value of gamma. So where does the distribution come in? It comes in the computation of gamma 0. That's the only place it comes in, okay? So if you don't know the distribution perfectly, you'll have a slightly offset cutoff value. Any other questions? Okay. Moving on to frequency selective fading channels. So when does frequency selective fading come in? This is the intersymbol interference problem when you're transmitting at high data rates, because the delay of the channel has to do with the speed of light and the increased distance of the delayed path to the direct path. So if you're transmitting at high data rates, that delay is typically going to exceed a symbol time, and you get frequency selective fading. So what happens in frequency selective fading, I no longer have this channel gain GI that is multiplicative. Now, across the entire frequency band of my channel, I have different gains. So H of F changes with F depending on the fading. So for a time invariant frequency selective fading channel, it turns out that the capacity is achieved using the same intuition as for the flat fading case. In the flat fading case, I adapted my power and rate in time. In the frequency selective fading case, I adapt my power and rate in frequency using the same water filling idea. So basically, now the water filling is 1 over H of F squared, where H of F is the channel gain at a particular frequency F, and it's varying because it's a frequency selective fading channel. The amount of power that I put into the channel is some constant level minus 1 over H of F squared. So it's a water filling idea. When I have a very poor channel in the frequency domain, I don't put much power. I don't put any power into it. So for example, here, H of F is small, which means 1 over H of F is large, so I don't put any power into the channel there. When the channel is good, H of F large means 1 over H of F squared is small. That's where I put the bulk of my power. And the way that you prove this, which is also the way you prove a lot of capacity results, is you decompose the frequency selective fading channel into a set of additive white Gaussian noise channels, static channels, via either a Karhunen-Loev decomposition, which is what Gallagher's book uses, or there's another paper by Hurt and Massey that uses just a DFT. So you take the frequency selective fading channel. Think about it as decomposing it using a DFT. So you get these different independent subchannels, okay? And BC is the coherence bandwidth of the channel, so the fading is approximately independent in each subchannel. The capacity of the entire thing is then the sum over the capacity in each of the independent subchannels. And you can prove that that is the capacity in a time invariant channel. When the channel's time varying, we actually don't know the capacity, but we can approximate it using the same idea. Chop the wideband channel into a bunch of independent flat fading channels, and then you optimize the capacity for that flat fading channel and take the sum. Interestingly, that's what OFDM does. So OFDM takes a wideband channel, breaks it up into a bunch of frequency flat channels, and does optimal modulation and demodulation on that. So this result says that OFDM is close to capacity achieving. It does achieve capacity on static channels, and we don't know the capacity in non-static channels, but you can show numerically that it approaches for any given block length the optimal rates that you can get. Okay. So now let me talk about some more exciting and recent stuff. So the result on frequency selective fading channels was in Gallagher's book, so that's from the 1960s. Let's talk about something more recent, like MIMO channels. So MIMO, which stands for multiple input, multiple output systems, was actually probably one of the most important advances in wireless communication over the last several decades. And the idea is that you've got multiple transmit antennas and multiple receive antennas. And if you know the channel perfectly at the transmitter and receiver, assuming this is a static channel, you can actually decompose that channel into a set of independent channels in the spatial domain. Okay, so you do a singular value decomposition on the matrix that defines the channel gains from each of the transmit antennas to each of the receive antennas, and that gives you a set of spatial channels. If the matrix of channel gains is not full rank, then rather than getting 3 independent spatial channels, I'll get a smaller number of independent spatial channels, which depends on how many non-zero singular values you have in the decomposition. Now, the beauty of MIMO then is that I go from one channel with a single antenna at the transmitter receiver to RH, where that's the rank of the H matrix of channel gains, independent spatial channels. So I get an RH fold capacity increase over the single input, single output system, single antennas, without increasing the bandwidth or the power. You also, when you know the channel at both the transmitter and receiver, get a significant demodulation complexity reduction, because each one of these channels just looks like an additive white Gaussian noise channel. Now, if you don't know the channel at the transmitter, then the receiver has to decouple all of these channels. So you get actually exponential complexity in the number of antennas. And so one of the big areas of research in communication systems is coming up with algorithms that reduce that complexity. But when you know the channel perfectly, you get a complexity reduction, similar to what we saw in the flat fading case. If you don't know the channel, you don't take a capacity hit, but you take a big complexity hit. You can also use the antennas for diversity or beamforming, where you optimally combine at the transmitter and receiver. Now, people that have worked in wireless a long time, when MIMO first came out, they're like, you know, we've used multiple antennas for decades. And it had been used for decades for diversity combining. So remember what I said about the flat fading. If you move a quarter of a wavelength, the phase is aligned differently. So if you optimally combine the signals that you receive, and the receive antennas are separated by a half wavelength, if one's in a deep fade, the other one won't be. So you can do optimal diversity combining. And so the fundamental question in MIMO systems, which hasn't really been addressed completely, is how do you use the antenna? So I'll talk about that in a second. Sorry, this is a duplicate slide. Okay. So when we talk about the capacity of a MIMO system, again, it depends on what's known at the transmitter and receiver. For static channels, if you know the channel perfectly at the transmitter and receiver, you just set up the same optimization problem that I've described twice already. So I talked about when the channel's changing in time, you do water filling over time. When the channel's changing in frequency, you do water filling over frequency. When the channel is changing in space, when you have multiple spatial channels, you do water filling over space. So basically, you optimize your power distribution to maximize the sum of the capacity of each of your spatial channels. Now, when you don't know the channel at the transmitter, we usually base capacity on the notion of outage, because the idea is that the transmitter doesn't know the channel, so it doesn't know the maximum rate that it will support. It's going to transmit at some rate, some fixed rate, say 10 megabits per second, and sometimes the channel, because it's randomly changing, sometimes it will support that, and sometimes it won't. So there's a notion of outage capacity in MIMO channels, which, even though that notion always existed in single-user channels, in the MIMO research, we've seen a lot more focus on outage capacity. Okay, now I mentioned beamforming. In beamforming, we have scalar code. So the idea is that you're doing optimal combining at the transmit side and optimal combining at the receive side. So you basically convert this channel into a single input, single output channel. And effectively what you're doing is you're transmitting along the best spatial dimension. So if you have a 3x3 system here, there's 3 spatial dimensions that you can transmit independent data of. Instead of doing that, you're going to focus all your power into the best of those spatial dimensions, and you transmit along that spatial dimension. So that's the notion of beamforming, and that can be optimal. Okay, so when would beamforming, when would picking only a single spatial dimension be optimal? Well, think about the water filling idea. Water filling says that you put the most amount of power into your best channels, you put less power into the worst channels, and some channels are so bad that you give up on them. So beamforming will be optimal when, say, you have 3 spatial dimensions. One of the spatial dimensions is really good, and the other 2 are really lousy. So if you did water filling, the lousy dimensions wouldn't get any power, and it would be optimal from a capacity perspective to put all your power into one dimension. Okay? And you can determine the optimality of beamforming based on, this is showing the variance or the mean of the singular values, and this is the covariance. So it's not, the details of this are not important, except that beamforming is not optimal when some of your spatial dimensions, when the spatial dimensions are more uniform in terms of their quality. So if you have multiple spatial dimensions and they're of roughly the same quality, it's not optimal to put all your power into one dimension. But if one spatial dimension is much better than the others, then beamforming is optimal. Okay, now I mentioned that there's this diversity versus multiplexing trade-off. So you can use your antennas for multiplexing or diversity. In the multiplexing case, you have 3 antennas and you send 3 independent spatial streams through those 3 channels that results. Why do I say that this is error prone? Well, it's not from a capacity perspective, because there are no errors in capacity. You drive probability of error to 0 when you're doing Shannon capacity. But if you look at this in the high SNR limit, and you look at the diversity multiplexing trade-off, where diversity is how the log of the probability of error over the log of the SNR scales in the limit of high SNR, we call that the diversity gain. So there is a notion of probability of error here. Intuitively, what that means is that when you do this matrix decomposition, so you've got a 3x3 channel matrix, and the signal-to-noise ratio on each of these spatial channels will depend on the singular value associated with the decomposition. So this will have the largest singular value, this will have the next largest, and this will have the smallest one. The reason I say that that channel is error prone is because in Shannon capacity, we're using very long channel codes to drive the probability of error to 0. But in a real system, the fact that this guy has a smaller signal-to-noise ratio than the other ones means it will have a higher probability of error. And that's captured through this diversity multiplexing trade-off. Instead of using my channels for multiplexing, if I use them for diversity, so I do optimal combining at the transmit and receive side, I only send my signal along the largest spatial, the best spatial dimension, then I'll have a low probability of error. So this diversity multiplexing trade-off was derived by Zheng and Say in the high SNR limit, and it's piecewise linear. So basically it says that the maximum diversity gain, which is over here, is equal to the product of the number of transmit and receive antennas. And this is very powerful because if you think about diversity gain, if you're just combining the antennas on the receive side, you get a threefold diversity increase. But if you have 3 on the transmit and 3 on the receive side, you get a 9-fold diversity increase. Your probability of error is raised to the 9th power instead of the 3rd power, so it goes down much faster. On the multiplexing gain, and again, I'm sorry this is cut off over here, the maximum multiplexing gain is the minimum of the number of transmit and receive antennas, because that's the maximum rank of the matrix. What Zheng and Shea showed, which was really interesting, is that the trade-off is piecewise linear. So you can pluck off as many antennas as you want. Suppose you start out with maximum diversity. You can say, okay, I'm going to take some antennas and use them for multiplexing, and you get basically a piecewise reduction in the diversity gain as you pull more and more antennas away for multiplexing. Now, what does that mean in terms of what's the best use of the antennas? I've told you what the mathematical trade-off is, but I haven't told you how the antennas should be used. So if I use them for multiplexing, the idea is that I have a very high rate channel, but I don't need to compress my image because I'm sending them over a high rate channel. So you make some errors. You can see there's a few black parts here, which is where I lose the bits that I'm sending over the error-prone channel. If I use them for diversity, then I don't make any errors, but I have to compress the image, so I get a fuzzy image here. And the question is, what's the best use of the antennas? And it depends on the end-to-end metric. So if I was viewing this image on my phone, which doesn't, I have a BlackBerry, so I'm really old-fashioned, I have a lousy screen resolution, I wouldn't notice that this was a fuzzy image, right? If you're viewing this on an HD TV screen, then you probably won't be happy with an image like this all the time. You would want to use your antennas for multiplexing. But you also won't be happy with errors. So when you're looking at this diversity multiplexing trade-off for a demanding application like a high-resolution TV screen, if you get too many errors, you still need the high resolution because that's what the person's paid for. If you get too many errors, you need to add more antennas. You don't have your system designed to meet the requirements of the application because there's no place on the diversity multiplexing trade-off curve where you can operate that satisfies the user. You either get low resolution or you get errors, and neither is acceptable. Okay, so kind of the main points so far in terms of MIMO systems, you exploit multiple antennas at the transmitter and receiver to get this capacity or diversity gain. If you have channel knowledge, then you can decompose the channel. Beamforming is optimal if you have one strong spatial dimension and other weak ones, and there's this fundamental trade-off between capacity increase and diversity gain. So let me spend like the next, say, 15, 20 minutes talking about multi-user channels, and then we'll take a break and move on to networks. Okay, so I already said in the multi-user channel case, we're trying to define these rate regions, the set of all rates that are simultaneously achievable. Now, we already talked about, just for the single user, that the capacity of the wireless channel changes depending on whether it's static with noise, or there's fading or intersymbol interference, or you have multiple antennas. So now we're making the problem harder because we still have all these different parameters, but now we have multiple users to worry about. So let's start with the broadcast channel. So the broadcast channel, just going back to the definition, broadcast channel is you have one transmitter sending to multiple receivers, and the multiple access channel is multiple transmitters sending to one receiver. Okay, so the capacity region in additive white Gaussian noise, say we have the simplest model, 2 users, so 2 receivers and 1 transmitter, and it's additive white Gaussian noise, so you have 2 receivers with a spectral noise density N1, N2, where N1 is less than N2. So one of the users has a better channel than the other, maybe it's closer to the transmitter. And again, we have to make some assumptions about power and bandwidth. So the transmitter has an average power P and a total bandwidth B. Both the bandwidth and the power now need to be allocated over the multiple users. So single user capacity, if I allocated all of my power and rate, or all of my power and bandwidth to one user, then he gets all the resources, the other user gets no capacity, and then I just have the single user capacity region. So these are the 2 extremes on the capacity region where you allocate all your resources to one or the other user. What are the achievable rates in between that? So you can look at this from a time division perspective, and I remember back in, actually the original work that I did on this was back in the 90s when everyone was talking about what's better, time division, frequency division, or code division. So we looked at the different possibilities from a capacity perspective. If you allocate time, so suppose that some fraction of time you allocate all your resources to one user, and then another fraction of time you allocate all your resources to another user, then you basically get the maximum rate associated with the power and bandwidth fraction of time t for user 1, and then fraction of time 1 minus t for user 2. And if you also allow yourself to vary your power, so if you vary the transmit power as well as the fraction of time you allocate the resources, then you get a rate region that looks like this, which is, again, the single user capacity region, or the time division capacity region. So you're allocating a fraction of time tau with power sigma 1, where the sum of power sigma 1 and sigma 2 weighted by the fraction of time you're transmitting that power satisfies the power constraint. So that's what it looks like. And you can do something similar for frequency division, where you allocate some of the bandwidth and some of the power to the different users, and you get a region that looks like this. And you can easily show that it's equivalent to time division, because basically what you're doing is you're chopping up the channel into orthogonal components in either time or frequency, and those are equivalent in theory. In practice they're not, but I won't get into that. Now, the capacity achieving strategy for the broadcast channel uses superposition coding. So the idea is that, remember that one of the users is better than the other. Okay, one of the users has less noise than the other user. So what the transmitter does is it transmits something that looks like a superposition code, where the user with the worst channel can't determine between the individual black bits in a quadrant. It can only determine the symbol that's in the middle, and it can only determine which quadrant the constellation comes from. Whereas the user with the better channel can actually determine which of those little black ones was sent. So the best user is going to decode the fine points here, so it gets the 32 QAM constellation data rate, and the worst user just gets which one of these 4 quadrants the signal was in, so it gets a rate associated with 4 PSK. So you can't really read the equations here, and they got a little messed up on the translation, so I won't show the well, let me just focus on this one here. So the thing that's magical about this superposition coding idea is that the user with the better channel completely gets rid of the interference from the other user. So it looks like that one doesn't even exist. It gets the capacity, B log 2 of 1 plus the signal to noise ratio associated with the amount of power allocated to the better user. Now the worst user, the one with the noise, basically sees the user with the better channel as noise, and that's the rate that you get. And if you look at the capacity, basically the code division, optimal code division is this line here, and this line, the straight line, is what you get with time division or frequency division, where you optimally allocate your power to the different users. If you don't optimally allocate your power in the frequency division case, you get one of these lines depending on how you do your power. And with time division, right, okay, so that will also give you the time division regions because they're equivalent if you don't optimize your power. Okay, so when we go to fading channels now, and I'm sorry about some of the pictures didn't integrate very well. Now I have the same fading channel as before, but in a multi-user setting. So now all of the users have fading on their channels. So remember what I said about the single user channels. The fading capacity depends on how you define capacity and what's known. So in the ergodic case, I'm going to assume that I can average the rates over the fading process. And basically what you get then is the capacity of the static channel averaged over the distributions of the different channels of the users. The delay, of course, will depend on the channel variation. So if you're a time-varying broadcast channel and you're using a superposition coding strategy and you have one user that's in a deep fade, that user is probably not going to get a lot of rate. while they're in a deep fade, because eventually they'll come out of the fade and then you send more power and rate to them. But if you happen to sit in a deep fade for a long time, you're going to have a large delay associated with your system. So these ergodic rates we're averaging over the fading process, and if that fading process is slow, it means that the delay for a particular user will depend on the channel variations. Now, we can change our definition of capacity and say we want to maximize the rate that we can send in all fading states. So this is similar to the notion of channel inversion. Channel inversion, I invert the fading so I maintain a fixed rate in all channels. Now I'm going to do the same idea of channel inversion, except now I'm doing it in a multi-user setting. So you can't just invert one user's channel in terms of your transmit power, because that affects the other user. So you have to do a joint optimization to make sure that both users maintain their fixed rates. And now remember that I said with channel inversion single user, capacity of the Rayleigh fading channel is 0. So we don't necessarily want to invert the fading or want to maintain a fixed rate in all channels, because some of the channels are really bad. So in that case, we maybe want to declare some outage. So we want to say a channel of one user or both users is so bad that we're not going to transmit. Okay, so let's just first look at the two-user fading broadcast channel. Basically, in that case, we can convert the fading into a time-varying noise. So you can show that it's equivalent to solve for the capacity of this channel, where there's no channel gain, but the noise is varying, the power of the noise is varying according to the channel gain. And then basically, to compute the ergodic capacity, you see the same formula in the case where you don't have any fading. So basically now I've extended this from 2 users to multiple users. So for the best user, they don't get any interference terms, but users with worse channels will have interference terms. So if I'm the user with the worst channel, all of the other transmissions to the other users will interfere with me. If I'm the user with the best channel, I get no interference. That's why we have this indicator function here. And the in-between users get some interference and some not. Okay, so we need to optimize the power constraint to maximize this region. And effectively, the superposition coding and successive decoding achieves the capacity. So we're basically using the ideas for static broadcast channels in each channel state. Now, in the case of outage, basically, it's a optimization problem where you need to find the power distribution that allows you to maintain the fixed rate of all users at all times. And again, that's challenging because you're not just inverting the fading of one user, because if you increase your power to invert the fading of one user, you cause more interference to the other users that have worse channels. So you have to balance out the optimization. It's a fairly complex optimization problem, but you can solve it. And you can also declare outage either for all users simultaneously or do it independently, and then it just becomes a more complex optimization problem. Finally, the last thing, so I've talked about the ergodic capacity, where basically you want to maximize the average rates to all users, averaged over the fading distribution. That's a problem if you have a delay-constrained application, because some users are in bad channels for a long time and they have to wait. The complete opposite strategy is to maintain fixed rates at all times. So what if we did some combination of the two? What if we said, okay, I've got users that have voice and data. Voice requires a fixed rate all the time. The data can vary depending on the channel. So that's the notion of this minimum rate capacity. The idea here is that you want to maintain some minimum rate, which is the minimum that your users are willing to accept, like voice. Then, if they have good channels, you maximize the data rate on top of the minimum on average. So if you do that, it's kind of a combination of inverting the channel to maintain the fixed rates and averaging over the good channels, so you put more power into the good channels and rate to get a higher average rate above the minimum. Okay, so I won't talk about the optimization of that, but this just shows if I have no outage, this is the rate region that I would get. If I allow myself to vary the rate over time, I get the ergodic capacity here. And the minimum rate capacity will be somewhere in between. If the minimum rate is equal to the highest rate that I get with the zero outage, then I don't do any better. But if I allow the minimum rate to be smaller, then I have more flexibility in taking advantage of the channel, and I increase my rate. Okay, now for multiple access channels, the problem's a little bit different. Now I have multiple users that are transmitting to a fixed receiver. And basically, the capacity region is defined by the sum of the rates of all the users in the system is less than b log of 1 plus this sum, which is like having all of the users combine their resources into one super user. So if you go back to the model for the Mac, the major difference of it is that you have different power sources for each user. So this will have some power source, this will have another, and this will have another. What the capacity result tells you is that the sum of rates based on any subset of the users is bounded by the capacity as if all the users pooled their power together, which is this sum of the powers of the users in the subset. And basically, the encoding order and the decoding order depends on the desired rate point. So this sum will trace out different curves depending on which subset you define, and that will give you the capacity region. And then you pick a point on the capacity region, and that will correspond to some decoding order. Okay, so this shows you the capacity region for the multiple access channel with 2 users. Basically, it's this straight line here, which is the capacity region that you get because you can decode up into this point. And then you have this region here, which is where the users are sharing the channel, and then this straight line here. So these are the two. Well, this is the region that's defined through the Mac channel. Okay. Now, I want to focus, the last thing I'll talk about before the break is a comparison of the Mac and broadcast channel and a notion of duality. Okay, so what are these channels look a lot alike, right? It's just that I flipped the arrows. So for the broadcast channel, I'm transmitting to the users, and for the Mac, I'm transmitting to the receiver. So what are the differences? In the broadcast channel, you have a shared power constraint. There's one power at the transmitter, which is shared among the users. In the multiple access channel, there's a near-far effect, which is the problem that if one of the users is much closer to the base station than the other, then the interference from this user will dominate what's received. That doesn't happen in the broadcast channel because the interference, say you're looking at this user, the signal to this user travels the same path. So there's no near-far effect. The similarities, though, is that in Gaussian channels, the optimal broadcast channel uses a superposition coding, and the Mac does the same thing. It's superimposing the coding for the different users on the same transmission. Both decoders also exploit successive decoding and interference cancellation in slightly different ways. So there's similarities in the encoding and decoding, but you have these kind of fundamental differences. So a question that we looked at is, can we somehow exploit these similarities to come up with new capacity results? So let's just first look at what's known in terms of the capacity regions. So for the multiple access channel, the capacity is known in many cases. It's generally boils down to a convex optimization problem. Whereas the broadcast channel capacity region is generally unknown. So it's generally an open problem unless you have degraded channels, which means that one user is better than the other in some sense. Or if you have parallel degraded channels where in, say, one spatial dimension, one user is better than the other, and in another spatial dimension, that same user is worse than the other. But you either need the channel to be degraded or parallel degraded. And the formulas are also often not convex. So even when we know the capacity region, it's hard to compute because we don't have nice, simple formulas. So we started to look at, is there a connection between the broadcast and Mac channel capacity region? And there is. It's a notion called duality. So we define dual broadcast and Mac channels as channels that have the same gains. So there's the same channel gains here. And the noise power is the same at each receiver. So the power of Z1, ZM is the same as the power in the broadcast channel, in the MAC channel, sorry. Okay, so what we showed is that if you have a multiple access channel, so this is the multiple access channel for an additive white Gaussian noise channel with some set of channel gains. And we showed that that capacity region is going to be contained in a broadcast channel region with the power associated with the broadcast channel, the sum of the individual power constraints for the MAC. So you can do this for different MAC channels, and you start to get the idea that if you took all MAC channels with the powers equal to this sum, you would sketch out the capacity region of the broadcast channel. And indeed, that's what we found, that you can get the broadcast channel capacity with power P and these channel gains as the union over all powers P1 and P minus P1, so all powers of the MAC that sum to the broadcast channel constraint and the same channel gains. Okay? So that gives us one connection. It tells us that we can get the capacity of the broadcast channel from a MAC channel where their powers are pooled. So this is the just showing the notion of pooling the powers. MAC channel with pooled powers gives you this broadcast channel capacity region. So they're the same. Okay, now what about going the other way, broadcast to MAC? Is it possible to get the MAC channel capacity from the broadcast channel? So here we want to exploit the fact that the MAC channel has this gain, square root of alpha times H1. And on the broadcast channel, we're now going to, so remember the broadcast channel has a fixed power. Now we're going to actually scale the broadcast channel power P1 by alpha. Okay? So if we do this scaling, the MAC channel capacity region is unaffected by the scaling. So remember, the broadcast channel depends on this notion of degradation. One user has to be better than the other. So as I change alpha, I'm going to change the degradation for the broadcast channel, but not for the MAC. So I can scale the MAC channel capacity. I transmit with power P1 over alpha, goes over a channel with gain root alpha H1. I get the same received power. It doesn't affect capacity. Okay, the scaled MAC capacity region is a subset of the scaled broadcast capacity region because of what I just showed before. This sum power constraint means that I can get the MAC capacity with the individual powers equal to that sum is contained within that broadcast channel capacity region. So the MAC region is inside the scaled broadcast region for any scaling. Now I look at the intersection of all possible scalings. Okay, so this is my MAC channel capacity. This is the broadcast channel capacity. All the blue lines are the broadcast channel capacity with this power scaling. So the broadcast capacity is affected by the scaling. If I take the intersection of all the scalings, I get the MAC. So this gives me a connection between the broadcast channel capacity region and the MAC channel capacity region. That's the duality notion. And you can actually get the, let me back up. So I won't show the slides for this, but you can actually get the optimal transmission strategy of one channel for the other. And the reason that's important is, remember I said that we often know the capacity of the MAC. The optimal transmission strategy is a convex optimization problem. We don't know it for the broadcast channel. So we can get it for the MAC and then do the conversion. Okay, this applies to different fading channels as well, all the definitions that I just described. So for example, you can do it for the minimum rate capacity. Okay, so what other capacity regions can be obtained by duality? I'm going to let us take a short break, I guess a 15-minute break. No, 15 minutes is good. So, and then I will tell you other uses of duality, particular for solving the MIMO broadcast channel capacity, and then we'll talk about networks. Okay.